Precision health really is our ability looking towards the future where we're going to be able to really look at each individual case almost like its own fingerprint and to apply the best mechanisms of treatment, minimize risk to patients, but also provide them with the highest level of efficacy that they may need for their particular disease. If you look at medicine really over the years, as our technological advancements have improved, whether it's MRI or blood work, we're able to kind of monitor progression of disease across various disease states in a much better way. More recently, with single molecule array technology specifically in what we do from a research standpoint, we feel like we're on the next cusp of being able to really individualize care for patients. And in our particular field, multiple sclerosis, that really is essential because the disease is very heterogeneous. Patients can have very mild disease requiring minimal treatment. Patients can have very severe disease requiring much more aggressive treatment. However, at the onset and for those first several years, you might not be able to really differentiate those two cases. So when you look at this on an individual basis for our patients, and the reason we're so excited about the potential application of this to the real world is really, can we change the natural history of someone's disease? And we believe that we can, and we believe that we're closer than we think. Saying that, it remains research-based, and we are doing everything in our power to really understand these proteins as much as we need to in the real world, really measuring it 10 times, cutting it once, trying not to extrapolate more than we need to. However, saying that our preliminary information is really optimistic. So we specifically use the Quanterix HD1 analyzer to look at neurofilament light predominantly. That's the main protein that we study. And we've been studying it in real-world multiple sclerosis patients as part of one of our research protocols. So we're doing a 5-year prospective research trial in real-world MS patients on a variety of MS treatments, really at a broad range of age as well. So we're able to really see what this may look like taking it from the bench, where we have some information and we kind of have some inklings of what it might mean, and really see what it looks like in real people who have other comorbidities, whether it's diabetes or they smoke, people who exercise, people who don't, and really try to figure out how we're going to be able to apply this in the most accurate way moving forward. So my understanding is that we're the first to use this prospectively in the U.S. In a real-world population. You have pockets of researchers, I think, that are looking at it for a variety of ways, but most of the information that we have on neurofilament to date is really retrospective. So you have patients who you have blood on from 20 years ago or 10 years ago, and then you're analyzing that blood and making some predictive measures based on where that patient is today, which is very useful. However, to get this to the next step, our research team as a group thought we need to apply this to the real world because that's really what we want, right? We want to be able to use this in patients in the future. Saying that, the responsibility is huge to get it correct. So we're very protective of it, I guess is what I would say. Protective of the interpretation of the data. We don't want to be superfluous with how we're interpreting it. But saying that, it's really been pretty profound to see this in real patients and kind of monitor patients over time over the last year. So our hope as a research team is, and our belief as a research team is that we don't think it's going to be an isolated individual biomarker that's going to be our predictive value. We believe it'll be a combination, kind of what we're terming and what you may have heard of as biosignatures. So we believe that patients have a particular biosignature, which is made up of certain ratios of various proteins, NFL being really the mainstay of that combination. And we're trying to figure out what that ratio may mean, what other proteins may matter, and to figure out how to apply that to the real world patients. And we're not just using, so it's interesting. So, in the ideal world, we would just be able to check blood and just be able to say, this means you need to do this. And I think we'll eventually get to that point. But I think the first step is to take the proteins that we have, figure out the ones that are very valuable, the ones that really have meaning for patients' disability progression, patients' cognitive change, patients' dexterity changes, and then to combine it with our currently available technologies like MRI to better understand kind of how these merge together. So we're looking at a variety of things. We're looking at proteins specifically, NFL, amongst others, and then adding to that things like atrophy measurements of the brain, spinal cord atrophy measurements, really looking at combinations and what they all mean together. From a patient standpoint, I think it's remarkably exciting. I mean, for for us, the ability for us, once we're able to really iron out the details of this, the ability for an individual patient to come in and for us to be able to really have predictive measures. And what we're focusing on is not just kind of information, right? So a lot of times we do research, we're just saying, oh, look, this correlates to this. Yay, that's nice. What we really want to look at is decision threshold information. So how much earlier in a disease state can I use this information to apply a change in treatment to prevent really a long-term problem that we will never know about at this point when we're able to do this. So MS specifically, I think, is a great disease state for proteins because it's a disease state that fluctuates significantly. You have two diseases really going on at once. One's inflammatory, the other one's degenerative. So you're trying to prevent both with treatment. And so I think protein marking is going to be, I believe that MS is really going to be the first push through in the neurology space, at least for protein marking. Things like dementia, I think, are very exciting, very predictive, but at this point we don't have really strong treatments at preventative care for those patients. So it's hard to see that applicability. But in MS we do. And we have drugs that are very mild in terms of strength and drugs that are much more powerful. However, some of those drugs have higher risks. So can I personalize your medicine to get you to the most effective risk-benefit ratio to prevent further breakdown of neuronal tissue? That's really the end goal of this. Neurofilaments are a part of a bigger protein complex that's really a heteropolymer. What that means essentially is that you have 5 proteins that make up kind of the scaffold or the backbone of neuronal tissue. So a way to think about this would be to imagine a home, okay? The roof of the home, the outside, the upper part, the roof, might represent something called myelin, which is kind of the insulation of a nerve cell. The house itself would represent the actual nerve cell, the way it runs, so kind of like a wire, so to speak. Well, underneath that house is what? It's a foundation. That foundation is the first part that's laid down. When you're building a home, you lay concrete down first, and then you build the home upon it. Well, neurofilament light and neurofilaments in general really represent that foundational aspect of the nerve tissue. So when we look at an MRI with our current technology, we can see the roof of the home, and we can sometimes see the actual house. But we can't measure really how much foundational loss is occurring underneath the home. And the ability to measure that, to really know what the structure and how strong that structure is moving forward, is where we think neurofilament is going to be the most important point. And so it's really exciting to be able to see microscopic changes of disease, whereas before we were really limited to MRI, which is great, but still macroscopic. So if we're looking at multiple sclerosis on an MRI, we might be seeing the disease from arbitrarily 10,000 feet. We believe with neurofilament testing and with protein testing, we're probably looking at this from 1 foot away.